So in kinetics, we're going to be looking at how fast a chemical reaction occurs, because the balanced equation tells us what happens, but it does not tell us anything about the speed of the reaction. So we start out by defining the reaction rate. So the reaction rate is just the change in concentration over time of a particular reactant or product. And we can only define a reaction rate for one species at a time. So for example, we can't just say the reaction rate of this reaction. We'd have to say the reaction rate, for NO2 or NO or O2. So here is a graph of the concentration of each of these species over time as the reaction progresses. And as you can see, NO2 is a reactant, so it starts out at a high concentration and then gets lower over time. Whereas the products, NO and O2, get higher over time. And NO gets higher faster than O2 because, as you can tell from the coefficients, the NO is being produced at a rate double that of O2. So it is convention to always use a positive reaction rate, even if the rate of change of the concentration is negative. So like here for NO2, even though the rate of change of the concentration is negative, we stick another negative sign onto it so that the rate becomes positive. And we can determine the relative rates of the different species in the reaction by looking at their coefficients. So say we know the rate of the reaction with respect to NO2. Well, we know that the rate at which NO2 is being consumed is going to be the same rate at which NO is being produced, since their coefficients are the same. And then O2 is going to be being produced at a rate half that of NO, because of the coefficient is half of the coefficient of NO. So if we're just looking at the Ford reaction, then the reaction rate only depends on the concentration of the reactants, not the products. And so this relationship is described by the rate law, also known as the differential rate law, because there are more than one type of rate law. So the reaction rate is equal to K, which is a rate constant specific to a particular reaction, and the K is always the same for that reaction. It can only change if the temperature changes. So multiplied by the concentration of the reactant to the nth power. Now N is what's called the order of this reactant. And the only way to determine both the rate constant and the order of a reactant is through experiment. So don't think that the order is always going to be just the same as the coefficient of that reactant in the balanced equation. They're different things. If the order is the same as the coefficient, then it's just a coincidence. So one way to determine the order of a reactant is to do what's called the method of initial rates. So you're seeing how the initial rate, which is just the reaction rate, like right when the reaction starts, you're seeing how this depends on the initial concentrations of the reactants. So let's say we have this balanced equation here, and so we can write the differential rate law like this. So you just take the concentration of each of the reactants and raise it to some power, which are the orders of these reactants, and that's what we're trying to find. So the orders are usually an integer, and in AP Chemistry you'll come across 0, 1, and 2 for the orders of a reactant. Now, the order can be a fraction or other number, such as 1.5, but 0, 1, and 2 are the most common. So, looking at this table, we have 3 different experiments in which we mixed different initial concentrations of the two reactants and then measured the reaction rate at soon after we mix them. So to find the order of one reactant, we're going to pick two experiments in which the initial concentration of that reactant we are trying to find was changed, but the initial concentration of the other reactants did not change. So let's say we're trying to find the order of NH4 plus in this reaction. So we're going to look at experiments 2 and 3, since the initial concentration of ammonium ion changed while the concentration of NO2 did not change. So we can put the data from experiment 3, the rate law here, over the rate law of experiment 2. So rate 3 over this rate is going to be equal to K times the initial concentrations of the reactants raised to their power, the order that we're trying to find. So when we do this ratio, the K's will cancel out, and the reactant where the concentration did not change, NO2 minus, will also cancel out. So we're left with 4 equals 2 to the n, and so we can see that n, the order of NH4 plus, is 2. So this reaction is second order with respect to NH4 plus. And so this is how the method of initial rates works out mathematically, but really for most of these simple problems, all you have to do is look at the data. So you see experiments 2 to 3, the initial concentration of NH4 plus doubled, the initial concentration of NO2 stayed the same, and the initial rate quadrupled. So if this reactant concentration doubles and the rate quadruples, it's going to be second order. Now, to find the order of NO2, we're going to look at experiments 1 and 2, since the concentration here changes, while the concentration of NH4 stays the same in these two experiments. So we look at these two experiments, the initial concentration of NO2 doubles, and the initial rate doubles as well. So we know that NO2 is going to be first order. Now, the other possibility, if the initial concentration changes, but the initial rate does not change, that means that reactant is going to be zero order. If a reactant is zero order, that means the reaction rate does not depend on the concentration of that reactant. So we've obtained the order of both reactants, so now we can write the differential rate law using the actual orders instead of these variables n and m. And so now that we found the orders, we can solve for K, the rate constant, by plugging in data from any of these three experiments. We just plug in all these numbers into the differential rate law and solve for K. And for this reaction, the units of K is molarity to the negative 2 times seconds to the negative 1, which it just means 1 over big M squared times S. And so the units of K are going to be different for every reaction. And so to find them, you just have to make sure the units on both sides of this differential rate law are equal. So the rate, since it's the rate of change of the concentration of a substance, the units of the reaction rate are always going to be molarity per second. And so you have to make sure the right side is also in molarity per second. So from the concentrations here, we have the concentration of this squared times the concentration of this. This gives us a total of 3 big M's. We have molarity cubed times K. So if we want the right side to equal molarity per second, we know we have to cancel out 2 of those molarities. And then we need to add a second on the bottom. So having this units cancels out 2 of the m's, from the m cubed here, leaving us with just m over s, molarities per second, which is what we want. And lastly, the overall reaction order of a reaction is the sum of all of the individual orders of each reactant. So in this reaction, the overall order is 3, because we have 2 plus 1.